Alright, this is lesson 17 of our term-long sequence of videos in circuit analysis. And today we're going to be looking at impedance and impedance combinations. Now, the last two videos, or last several videos, were more math-heavy with kind of a disregard for circuits. And in this video, we're going to start to bring together now the math with the circuits. Let's get started, and we've been looking at sinusoids, and we're going to be very heavy on sinusoids from here on out. Why are we so interested in sinusoids? Well, this question is typically not answered in EE1 courses. At least it wasn't in mine. And I want to first take some time to explain the answer to this very important question. Why are we so... We so is two words, of course. Why are we so interested in sinusoids? Right, well, you might know that your wall outlet is a 60 hertz sine wave. Why are we so interested in sinusoids? Well, first of all, you should know that there was this mathematician, engineer, scientist, Fourier, and he said that you can express any waveform, so a voltage waveform or a current waveform, as a summation of sinusoids. So I'm going to write that down. Any waveform, so here we're talking about voltage or current, but any shape, really. Okay, so some odd-looking waveform, any waveform can be expressed as a sum of sinusoids. Okay, so for example, you have some odd-looking waveform that's a voltage. Call it V of t. Well, it turns out you can write it like A1, some constant A1 times sine of some frequency, omega 1, plus some phase, phi1, plus another sinusoid, call it A2, sine of omega 2 plus phi 2 plus A3 sine of omega 3 t plus phase 3, and so on. Any waveform can be expressed like this. If you know your Fourier analysis, then the Fourier analysis tells us what these constants are, what these amplitudes are, A, what these frequencies are, omega, what these phis are, the phases, phi, and how many of these waves we need. Okay? Now, this class does not cover Fourier analysis. Okay, so you will not learn the ingredients, right? The A's, the omegas, the phis. Okay, but you should know that this result exists, that we can write any waveform as a sum of sinusoids. Okay, that's number one. That's a very powerful thing there. And number two, we know already that the circuits that we're looking at in this course are linear circuits. And linear circuits can be analyzed with superposition. Okay, just to refresh your memory, if you have multiple sources, superposition allows us to turn off all of the sources but one, find its contribution to the circuit parameters, and then find all of the contributions from each source individually and add them together. Right? So now let's put these two things together. If any waveform can be expressed as sinusoids, a sum of them, and superposition holds, meaning we can just find the contribution from this guy, and then we can find the contribution from this guy, and find the contribution from this guy, and add them up, then all we really need to do is figure out how our circuit behaves from a sinusoid, one of them. This is why we're so interested in sinusoids. Now, what I want to do is demonstrate this first thing to you, that any waveform can be expressed as a sum of sinusoids. I'm going to use a square wave because I know off the top of my head what its ingredients consists of. So, what is this A1, what is this A2, what is this A3? So I've written a computer program, and we're going to look at that, and that should demonstrate to you, yes, in fact, Fourier's theorem is correct. Okay, this code is going to demonstrate how we can construct a square wave of frequency 440 Hertz by summing many different sinusoids. So let's start by making a plot of our first sinusoid, xt here. So this has got an amplitude of 4 over pi and a frequency again of 440 Hertz. And here's the plotting command. Now, I have a loop here. II, the iterator, is going to go from 3, count by 2s, all the way up to 1001. So it's going to be, II is going to be 3, then 5, then 7, and so forth. And each time it runs through the loop, it's going to add to our x of t a new sinusoid. So for instance, when II is equal to 3, our new sinusoid will have a frequency 3 times 440 Hertz, and an amplitude of 1 over 3 times 4 over pi. Now the details you don't have to know, right? Why is this 4 over pi times 1 over 3, and so forth? This is coming from Fourier's theorem. But what you do need to know is that for every loop, we add to it a new sinusoid, and that becomes our new xt. Now, when II is 3, so the first time through the loop, I ask it to make a plot of another figure. So let's see what that looks like. So here you see a second sinusoid superimposed on the first sinusoid. The second sinusoid is smaller in amplitude and has a larger frequency. Now, back to the code, it loops back up again, and II is 5, and it adds a new sinusoid to our x of t. And because II is 5 here, I've got it plotting this function. So now, look at the plot. Now we have 3 sinusoids, and you see a third sinusoid superimposed on the second plot. That makes the third plot. And you see the new sinusoid has a higher frequency and a smaller amplitude yet. Now back to the code. I don't want to plot all of these sinusoids, but when II gets to 101, we're going to make another plot. Let's see what that looks like. Alright, so that corresponds to 51 sinusoids. 51 because II is going up by 2s. So when II is 101, that makes it 51 sinusoids. So you see now, including 51 sinusoids, it starts to look like a square wave, definitely. Back to the code, it'll loop some more now. And when it gets to 1001, That's the last sinusoid I wanted to add to it, and it's going to make another plot. So here it is. All right, so that's 501 sinusoids added together. Now, for all intents and purposes, this is a square wave now. That's why I decided to stop it at II equals 1001. So this is a square wave, so Fourier's theorem holds. We made a square wave by just adding sinusoids together. Again, the details, why is this II times F0 and why is this 1 over II times 4 over pi, you don't need to know. That's the recipe that Fourier established. Okay, now that we've seen the importance of sinusoids in electrical engineering, let's investigate what happens when a sinusoidal voltage, maybe we'll call it V of t. Okay, what happens when V of t is connected to, well, we'll start with a resistor, R. And for this example, let's say V of t is a sine wave, so it's got some amplitude, some frequency, and maybe some phase, but we'll leave the phase to be 0. Right? So here's our sine wave, and we're interested in the current. What does the current look like? Well, mathematically, okay, Ohm's law still has to hold. So we know that V equals I times R. So here we've got V of t equals I times R. And so I is V of t divided by R, right? It still must be true, right? The physics don't change just because we have, a sinusoid. So this is now Vm over R times sine of omega t. Here's our current. So this thing is also a sine wave, right? So a couple points here. Notice that the amplitude of the current, is Vm over R. Right? That is to say, the amplitude of the current is the amplitude of the voltage divided by the resistor. All right, that's point 1. Point 2 is the frequency of the current is still omega, right? So the frequency of the current is the same as the frequency of the sine wave, of the voltage. The frequency does not change. That's very important to linear circuit analysis here. 3, the phase of the current, well, it's still 0, right? But we'll say the phase of the current is the same as the voltage, as we'll say as that of the voltage. So we gave our voltage waveform 0 phase, and our current waveform has 0 phase. Okay, so to summarize here, the resistor did not change the frequency of the sinusoid, and it did not change the phase. It did change the amplitude, as you would expect from Ohm's law. All right, let's look at a plot of these guys. So here's t, and in blue I'll have V of t. So I chose a sine wave because a sine wave goes through 0, 0, right, with no phase. And then it reaches its maximum, comes back down, its minimum, and so on, right? So up here is Vm, down here is minus Vm. So let's make a plot of the current that's also a sine wave. So the axis for current, of course, is amps, so we don't want to compare the amplitudes because the axis for voltage is volts. But here, now in red, this is Vm over R, and this is minus Vm over R, right? So notice here the zero crossings happen in the same positions of time, and if I drew the wave correctly, I guess I'm off a little bit, the maximum of the current should coincide with the maximum of the voltage, and the minimum of the current should coincide with the minimum of the voltage. This is to say, of course, that the phase of the current is the same as the phase of the voltage. So all of these points line up with one another. The zero crossings, the maxima, the minima. Also, the wave goes up and down at the same frequency as the blue wave, right? So that's 0.2. And again, we've already mentioned the amplitude is Vm over R. That's 0.1 here. Now, I want to point out at every slice of time, so maybe this time here, at every slice of time, Ohm's law must be satisfied. So the voltage right here divided by the resistance gives you this point. Okay? At the zero crossings, the voltage is 0. So voltage divided by the resistance gives you 0, and so the current is 0. When the voltage is a maximum divided by resistance, that gives you a maximum current. Every slice of time, every instantaneous slice of time, V equals IR. It must be true. All right. Let's move on to the capacitor. Okay, so again, we'll say we have a sinusoid where the voltage is equal to some maximum times sine of omega t. And we've got that voltage source connected to a capacitor this time. And we want to know what's the current through the capacitor. Well, we said that the current through a capacitor is C dV dt. I equals C dV dt, right? All right, so with the sinusoid then, this is C times the derivative of this guy. So when I take the derivative of sine, right, that changes into a cosine, and then from the chain rule, the omega comes out in front. Cosine omega t, right? So this is another sinusoid. And let me make a few corresponding points on the capacitor here. Number one, the amplitude of the current is C omega Vm. So take the amplitude of the voltage, multiply it by C and omega, the frequency, and that is our current. So this is different than what we saw with the resistor. The amplitude of the current in the resistor did not depend on the frequency. Okay, so I'm just going to write here frequency dependent. That's an important point here. So we can get more current by just changing the frequency, raising the frequency. 2, the frequency of the current sinusoid remains unchanged at omega. Is omega. So we'll write the same as the voltage. Now, our voltage source was a sine wave. Here, from the derivative, the current is a cosine wave. So those guys are out of phase by one another, or of one another by pi over 2. So we'll write the phase of the current is pi over 2 radians, right? And we're going to come back to that in a second, but let's make a plot now of these guys. So in blue again will be the voltage. Right, so this looks like this. Again, Vm minus Vm down here. And let's plot the current. So the current is this this waveform here. So it's going to go, but notice when t is 0, cosine of 0 is 1. And so we're at our maximum. And then it comes down. So I gotta be careful how I draw this a little bit. Something like that. So this peak is C times omega times Vm. Right, this peak down here, or the minimum, is negative C omega times Vm. What's this value? Right? Notice when the voltage has its 0 crossing here, the current is at its maximum. And when the current is at a 0, the voltage is at its maximum. Now here the current is at a minimum, and the voltage is at a 0. And here the current is at 0, and the voltage is at a minimum. All of this is to say, again, this point 3, the current and the voltage are out of phase by one another by pi over 2 radians. All right, and which waveform here is leading? Well, we talked about this a couple videos ago, and it looks to me like the red is leading, right? Because, for instance, the red hits its downward going 0 crossing first in time, and then the blue wave hits its downward going 0 crossing a little bit later. So the red is leading, the red is the current, so the phase of the current is pi over 2 radians and leads the voltage. Or equivalently, the voltage lags. Alright, so again, you want to compare this to the resistor. The resistor, we saw no such phase difference there. Alright, now consider, I'll just change the picture. Alright, let's leave it, I'm sorry. Let's just draw a picture down here. Now let's consider the inductor. And suppose we had a current source. Call it I of t. And that I of t had some maximum. And it was a sine wave. L. And we want to know what is the voltage. What's the voltage across the inductor? All right, well, we know with an inductor the voltage is L di dt. Right, so that would be L times the derivative of this guy. Again, we would get omega Im cosine omega t. So a couple points about this. First, the amplitude of the voltage is L omega Im. Okay, again, that's frequency dependent. Two, notice that the frequency of the voltage is the same as the frequency of the current. So we'll write frequency of voltage is omega, same as current. All right, 3, squeeze it in down here. Well, here we have a cosine, here we have a sine, so the phase of the voltage is pi over 2 radians. And this time, the voltage leads the current. All right. Let's summarize these 3 components, the resistor, the capacitor, and the inductor. Okay. So we'll put resistor here. Okay, and so the amplitudes in a resistor are related by Vm equals Im times R. So this row will be the amplitudes. And in a capacitor, the amplitudes are related by Vm was Im divided by omega c. In an inductor, the amplitudes are related by Vm equals Im times omega L. All right, the frequency doesn't change. The resistor does not change the frequency. The capacitor does not change the frequency. An inductor does not change the frequency. That's good. The phase. The phase of the voltage and the current were the same. Okay, so I'll write delta phi equals 0. Here, we'll say that we'll because we're working with V equals IR, we'll consider the voltage. For the capacitor, the voltage leads. The voltage lags by pi over 2 radians. And for the inductor, the voltage leads by pi over 2 radians. Okay, all 3 of these are very important for our circuit analysis to come. Okay, now, life was good. Life was good when we just had resistors. All right, and we were just able to use this equation, V equals IR. That was nice. And then along came the capacitor and the inductor, and we had to start considering derivatives and integrals, etc. Wouldn't it be great? Wouldn't it be really nice if I could just use Ohm's law for capacitor and the inductor? You know, maybe I could use an equation, maybe not R, but some constant, we'll call it Z, where if I knew this Z, I could just use this equation. That would be really nice. Can I do that? Can I just use this equation? Well, it turns out you can. We can find a Z for the capacitor. So I can use just Ohm's law, good old Ohm's law. Let's check it out. Capacitor. So we're going to say we want to express our voltage as the current times some number Zc. C stands for capacitor. So now, let's suppose it's more convenient to write in terms of a phasor now. Let's suppose the voltage across a capacitor was Vm e to the j omega t. Remember, that's a sinusoid. Well, we know, again, that the current must be c dv dt. Right, so this turns out to be c, and if I take the derivative of the voltage, the j omega comes down in front from the chain rule, and I get this. So let me plug these guys into this Ohm's law, thing we're calling Ohm's law. So on the left I have V, so that's Vm e to the j omega t. And on the right my current is C Vm j omega e to the j omega t. And then I have this Zc that I don't really know what it is yet. But notice here now Vm cancels, e to the j omega t cancels. On the left I have 1, and on the right I have j omega c times Zc. So that says to us, this is great, good news, that if I'm going to use this equation, I can find a Zc actually. It's 1 over j omega c. This is great news. Now I can use Ohm's law for a capacitor, and this thing, Zc, that's playing the role of the resistance, that thing is 1 over j omega c. It's imaginary, right? 1 over j. But it's going to allow me to find the voltage or the current algebraically instead of using calculus. More on that in a second. But let's come to the inductor now. And again, can I write V as I times some number? We'll call that number ZL. Can I do that? And turns out I can. Let's consider we have a sinusoidal current through our inductor. Like that. And we know that in an inductor, the voltage is L di dt. So this is L times Im. The j omega comes down in front from the derivative chain rule, e to the j omega t. Right, so now plugging this into our Ohm's law equation, I have on the left L Im j omega e to the j omega t, and this is equal to our current Im e to the j omega t times this ZL thing. Alright, notice the Ims cancel, the e to the j omega t cancels, and I'm left with, on the left, j omega L equals ZL. Voila! So this says I can, in fact, express the voltage and current algebraically, but, so I don't need to use calculus, but the trade-off is that this thing that's playing the role of the resistance, ZL, that's imaginary. It's j omega L. So our choices are to use derivatives and integrals or to use complex numbers. We're going to choose to use complex numbers. Now over here, notice the magnitude for the capacitor now. Capacitor, the magnitude of Zc, or the magnitude of this thing, is 1 over omega c. Notice the phase of this thing. Well, remember, 1 over j is like minus j, so the phase is minus pi over 2 radians. Right? And over here for the inductor, the magnitude of this thing is omega L, and the phase of this thing is pi over 2 radians. Now, here's where it should lock in for you. Look at what we set up here in this table. Here's how the voltage was scaled. Take the current and scale it by omega c, or 1 over omega c for the capacitor. And look at what we have here. Now, take the voltage. Okay, the voltage lags by pi over 2 radians. Lags, too, is the key. And what's the phase of a capacitor's? Z minus pi over 2 radians. That's not a coincidence. Now for the inductor. What was the current scaled by to get the voltage? Omega L. What's the magnitude of this inductor's ZL? Omega L. For the phase, the voltage leads by pi over 2 radians. And what was the phase of ZL? Pi over 2 radians. So you see, we can use complex numbers to keep track of how the voltage amplitude and the current amplitudes are related. That's going to be related to the phase, the magnitudes of these complex numbers. And we can keep track of how the voltage and current phases are related. That's going to be related to the phase of these complex numbers. And what about the frequency? Well, we don't even have to keep track of the frequency because the frequencies don't change. So we're going to use complex numbers here to keep track of the amplitudes and the phases simultaneously, because complex numbers have magnitudes and phases respectively. Now, one more thing before we look at some examples. One more thing here. This thing that's playing the role of the resistance, this ZC and this ZL, this thing is called impedance, right? So here's the title now of our lesson, impedance and impedance combinations. In general, now we've unified the theory or the analysis for each of these three components. We're using the equation V equals IZ. It's just that for a resistor, Z equals R, the resistance. For a capacitor, Z is 1 over j omega c. And for an inductor, Z is j omega L. So now, no matter which component we are analyzing, we can use this equation if we plug in the correct Z. So this whole time, what we've been calling a resistor, okay? Well, here's the universe of resistors. Okay, but that is just a smaller part of a much larger universe of impedances. In general, an impedance introduces a change in amplitude and a change in phase of the waveforms. Right? That is to say, in general, impedances have magnitudes and phases, but the resistor is a special type of impedance. Impedance. It's an impedance that is purely real, right? It has a phase of 0. All right, let's look at some examples now. Well, I've got this first example for you. So we've got a voltage source here, and its voltage is 10 cosine 1000t plus 30 degrees. And we want to find the current through this 10 millifarad capacitor. Now, you could use I equals C dV dt. You could use that. However, when the circuits become a little bit more complex, right, this is a very simple circuit. When they become more complex, you're not going to want to be solving systems of differential equations. You're going to want to solve algebraically via complex numbers, the voltage current relationships. So let's use our new tool now to do so. All right, well, notice our voltage source is at 1000 radians per second. Frequency. So that makes the impedance of the capacitor 1 over J times 1000 radians per second times C, which is 10 times 10 to the minus 3 farads. Okay, so this is the minus 3 here cancels with the plus 3 here. So this is 1 over J10 ohms. So ZC is, now if I bring the J up, remember dividing by J is like multiplying by minus J, and 1/10 is of course 0.1. So this is minus J 0.1 ohms. So I'm going to redraw this picture, right? And I'm going to keep track of the amplitude 10 volts and the phase 30 degrees, but not really the frequency, because I know the frequency is not going to change. So I'm going to write 10 angle 30 degrees. That's my voltage source. 10 angle 30 degrees, and here instead of labeling the capacitance, I'm going to label the impedance like that. And actually, notational wise, you'll see that the I in some texts, I think your book does this, now it becomes capital to show that you've changed it. This is called the time domain picture. You've changed it from the time domain picture, and this is called the frequency domain. This is now the frequency domain, so we use capitals over here. All right, so we can use Ohm's law. We've got V, which is 10 angle 30, equals I times Z, which is minus J 0.1 ohms. So I is V over Z, which is 10 angle 30 divided by negative J 0.1 ohms. Now this is math, right? We said that division is best done in polar or exponential form. So the numerator is already in polar form. Let's get the denominator in polar form. Minus j, 0.1. So this has a magnitude of 0.1, and a phase, minus j is down pi over 2, or 90 degrees. So negative 90 degrees. There. So the current, if I do this division, then 10 divided by 0.1 is 100. And remember, the angles subtract. So 30 minus 90, 30 minus negative 90 is 120 degrees. Amps, right? So now let's convert this back to the time domain. I of t is 100 cosine, because we started with a cosine. The frequency does not change, and the phase was 120 degrees amps. This is the current. Neat, huh? Alright, let's do this again. Let's do this again with another example. Alright, let's say we have another simple picture for right now. Let's say we have 10 cosine of, or let's do sine. 10 sine of, let's say, 200 t plus 10 degrees, and this is a current, and this goes through an inductor of inductance, we'll say 5 millihenry, and we want to find the voltage across it, V of t. Right? Find the voltage across the inductor. Alright, so this is the time domain picture. Let me just point out to you that the frequency is 200 radians per second. So I'm going to convert, so I've got that, so now let me find ZL. Okay, ZL is J omega L. So this is J times 200 radians per second times 5 millihenry. So 5 times 200 is 1,000. 1,000 times 10 to the minus 3 is 1. So this is 1, and then we have the J. So this is J ohms. Now let me convert this to the frequency domain picture. So my current source was 10 amps angle 10 degrees. 10 angle 10 degrees. And instead of labeling the inductor, or the inductance, I'm going to label it by its impedance, J ohms. And here's the voltage I want. I'm going to give this capital V. Alright, so again, here's the beautiful part. I can use V equals IZ, Ohm's law. Right. So this is 10 angle 10 degrees times J ohms. This is really, I left off the unit here. This should be 10 amps angle 10 degrees times J ohms. Alright, well, multiplication is best done in polar or exponential form. So this is 10 amps angle 10 degrees times J has a magnitude of 1 and an angle pi over 2, or 90 degrees. Right? So when I do the multiplication, I've got 10 amps times 1 ohm. That gives me 10 volts. And I've got 10 degrees plus 90 degrees. That gives me 100 degrees. So the voltage back in the time domain is 10, and I started with a sine, so I'm going to keep that. The frequency does not change. Plus 100 degrees volts. There's the answer. Again, neat, right? Very neat. Alright, let's move on. Now we're really getting into circuits. Here's the beautiful part. Because we've unified all three components, the resistor, the capacitor, and the inductor, with this simple equation, all of our tricks that we've learned for just the resistor still hold now, right? Because this is still a linear equation. So all of our linearity tricks work. So let's think of all those tricks that we learned, right? First of all, Kirchhoff's laws. KVL, KCL, right? We learned that with the resistor. We learned resistor combinations, right? Series and parallel combinations, we'll say. Parallel. And delta Y. All right, combos. And as a corollary to that, we saw voltage and current division. Ooh, everybody's favorite, mesh and nodal analysis. And these are just some of the tricks we learned. Thevenin Norton, linearity, the list goes on. Wow, we've covered a lot. Linearity, superposition, source transformation. What else? Maximum power. Alright, that covers most of it anyway. All of these things, this long list, still hold true simply because we can relate the voltage and the current by a linear relationship. So these all hold true even with the capacitor and the inductor. And we will look at some of these in this course, in the remainder of this course. And right now I want to look at series and parallel combinations. So I'm not going to prove it because the proof is very similar to that for resistors. But if you had, let's say, Z1 in series with Z2, in series with all of these impedances, Zn, you could replace all of those things with a single impedance, Zeq, which would be Z1 plus Z2 plus all the way to Zn. And more compactly, that's a summation J. J is not the best letter anymore. How about K equals 1 to N of Zk. So series impedances combine just like series resistors combine. Also, here's Z1, here's Z2, all the way to Zn. Parallel impedances can also combine and they combine in the same way that parallel resistors combine. Again, because the Z is playing the same role, right? It's playing the role of the resistor. So this would be 1 over Z1 plus 1 over Z2 plus all of these things, Zn inverse. And there is a similar combination for delta Y. I'll let you read your book about that. Now let's look at an example. Alright, let's take a voltage source of 20 cosine 4t minus 15 degrees volts connected to a 60 ohm resistor and a 10 millifarad capacitor. 10 millifarad capacitor and a 5 Henry inductor. We want to find the voltage across the inductor, or across the capacitor too, because those are in parallel. Alright? Find V of t. Alright. First of all, notice the frequency of our source is 4 radians per second. So that makes the impedance of the capacitor 1 over J times 4 radians per second times 10 times 10 to the minus 3 farads, which gives us, let's see, so this is 10 to the minus 2, so this is J times 4 times 10 to the minus 2. So bring the 10 to the minus 2 up, makes 100. 1 over 4 is 0.25, so this is 25 over J ohms. And if we bring the J up, this is minus J 25 ohms. The impedance of the inductor is J omega L. So this is J times 4 radians per second times 5 Henry. So this is J 20 ohms. And what's the impedance of the resistor? Well, remember, that's just 60 ohms. 60 ohms. So now let's transform this into the frequency domain. 20 angle minus 15 degrees. $60 ohms. And instead of labeling the capacitance, I'm going to label minus J 25 ohms. And instead of labeling the inductance, I'm going to label its impedance J 20 ohms. Right? And where is that V that I'm looking for? That's this guy. I'm going to write capital V. Alright. Now, as we've already said, the inductor and the capacitor are in parallel because they're connected to the same two nodes. So I can combine those guys. Right, so this gives me, again, 20 angle minus 15 degrees, 60 ohms. And here I'm just going to draw a box. I'm going to label its impedance. And the equivalent impedance of these two things is, well, when two things are in parallel, I can do the product over the sum. So the product of those, when I take J times J, I get minus 1. Minus 1 times the minus 1 gives me positive 1. So I've got 20 times 25 over the sum of those two things. J20 minus J25 gives me minus J5 ohms. So I've got, what is this, 100 over minus J ohms? Yes. And so this, if I bring the J up, it makes minus, so this makes positive 100J. All right, so I'll put that in my picture. And when you combine in parallel, of course, the voltage is the same, so this is the voltage that I'm looking for. So how can I get this voltage quickly? I've got the voltage across a series combination. So what still applies? Yep, voltage division. Alright, so V I can get using voltage division. This is 20 volts time, with an angle of negative 15 degrees times the impedance whose voltage I'm interested in. So that's this guy, J 100 ohms, over the sum of the two impedances. That would be 60 plus J 100 ohms. I'm gonna erase some of this to give us some space. All right. Well, I've got multiplication and division. So both of those things are best done in polar or exponential form. But let me show you a trick. If I multiply this thing by its complex conjugate of the denominator, then something nice happens. So let's do that. Right? I can multiply this by 60 minus j over 100, or 60 minus j 100 over 60 minus j 100. That's like multiplying by 1. So the reason I would do this, if you did a similar thing in high school, it's the same. Notice the denominator, right? Gives me, I get 60 times 60, which is 3600. The cross terms actually cancel, and I'm left with the last terms when I FOIL this out. Minus j times plus j gives me plus 1, and I get 100 times 100, so that's 10,000 in the denominator. So see, when I did this, when you multiply by a complex number by its conjugate, you get its magnitude squared, right? So it's purely real. And then in the numerator, I get j 100 times 60, so that makes j 6,000. And then j 100 times minus j 100, that makes plus 10,000. Okay, I'm going to bring it over here on the left. So this is now 20 volts, angle negative 15 degrees, times 10,000 plus J 6,000 ohms, right? Or no, the ohms will cancel then, because it's a fraction. And then in the denominator I have 10,000 and 3,600, so this is 10,000, so 13,600. So we've got V now is equal to, and I can certainly divide 10,000 by 13,600, and I can divide 6,000 by 13,600. Right? I don't normally like to show the math calculations in these examples, but since we're reviewing complex numbers, let's do it. So we'll do 10,000 divided by 13,600. Alright, so that's 0.735. 0.735. 0.735, and then we'll do the imaginary part. Okay, so this is 6,000 divided by 13,600. 0.441. 0.441, I think. Yes. Okay. So now our voltage, again, we have a multiplication. So I want to convert this, that's in rectangular form, to polar form, so I need its magnitude. So I need the square root of this guy squared. So let's do this result, and let's square it. Okay, 0.194. So this is the square root plus 0.194. And then we need the angle as well. So let me do 0.735 squared. Okay, and then I'm going to add to that 0.194 equals, and take the square root. Okay, 0.857. So this is 0.857, and I need that angle. Okay, so the angle of this thing, so I'm going to take 0.441 divided by 0.735, gives me this, 0.6, and I need the inverse tangent of that thing. Do I have the inverse tangent on this? Okay, I don't. Alright, so I need the inverse tangent of 0.6. We'll just write it like this. The inverse tangent of 0.6. Alright, so now when I do the multiplication, (20 times 0.857), 20 times 0.857 gives me 17.1 volts, and then my angles add, so I've got negative 15 and the inverse tangent of 0.6. So we'll just say inverse tangent of 0.6 minus 15 degrees. And so the answer in the time domain is 17.1 volts cosine, because I have cosine here, 4t, the frequency does not change, with an angle inverse tangent of 0.6 minus 15 degrees. That's the answer. So the calculation of 17.1 looks good, because here we have an amplitude of 20, and we know it gets divided, so we shouldn't expect more than 20 volts peak. Right, so we've got a 17.1 volt peak. That looks good.